Quantum computing. Yeah, I know, it sounds like something straight out of a sci-fi movie, right? But what if I told you it's not that different from the computer you're watching this on? Well, kind of. Today, we're going to peel back the layers, go right down the stack, from the wild ideas at the top, all the way to the nuts and bolts, to see what really makes these things tick.
All right, so here's our game plan. We're going to look at the new computing paradigm, then the quantum instruction set, the algorithms that run on it, the hardware race to build it, and finally, we'll bridge the gap back to reality. Let's do it.
Okay, kicking things off with a new computing paradigm, beyond bits and bytes. And this is super important to get right off the bat. A quantum computer is not just a faster classical computer. It's a whole new ballgame, playing by a completely different set of rules. So let's start with this question. What if a computer worked with probabilities, not just ones and zeros? I mean, think about it. Your computer right now thinks in absolutes. A switch is on or it's off. A bit is 1 or it's a 0. But what if it could be both? What if it existed in this hazy, in-between world of possibilities? That's the fundamental shift we're talking about.
And this leads to probably the biggest myth in all of quantum computing. You've heard it, right? It tries all the answers at once? Well, not really. It's much, much cooler than that. The real magic isn't parallel processing, it's interference processing. The whole idea is to make the wrong answers literally cancel each other out, so the right one just pops out.
Okay, so how does that even work? How do you make answers cancel out? Well, for that, we have to go a layer deeper in our stack, down to the quantum instruction set. This is where the physics really starts to power the logic.
And at the heart of everything is this little guy, the qubit. It's the quantum world's answer to the classical bit. But here's the twist. A regular bit is stuck. It has to be either a 0 or a 1. A qubit? A qubit can be a 0 and a 1 at the exact same time. We call that wild state superposition. So superposition is the state where a qubit is a mix of both 0 and 1. And that mix is described by something called amplitudes. You can kind of think of them as weights, telling you how much 0 and how much 1 is in the mix. When you finally look at the qubit, or measure it, the probability of it being a 0 or a 1 depends on these amplitudes. It's like a quantum coin spinning in the air before it lands. Now here is the secret sauce. This is the absolute key to everything. These amplitudes can be positive or negative. And because they can be negative, they can do something amazing. They can cancel each other out. This is where that interference thing comes from. You can have constructive interference, where amplitudes add up and make an answer more likely. Or you can have destructive interference, where a positive and a negative amplitude for a wrong answer meet and, poof, they wipe each other out. That's how we get rid of the noise.
And if you thought that was weird, hold on. Let's talk about entanglement. This is where two qubits can become linked in this spooky way. Their fates are completely tied together. It doesn't matter if they're next to each other or on opposite sides of the galaxy. If you measure one and find out it's a 0, you instantly know the state of the other, no matter what. It's like having a pair of magic coins. If you flip one and it's heads, you know without looking that the other one is tails. Instantly.
All right, so we've got our building blocks, superposition and entanglement. Let's move back up the stack to the algorithms. How do we actually use this stuff to do something useful? This is all about orchestrating that interference.
Yeah, that's really the best way to think about it. A quantum algorithm is like a symphony conductor. Its job is to carefully orchestrate all those positive and negative amplitudes. You want to set it up so that all the paths leading to the wrong answers cancel each other out, while all the paths leading to the right answer all add up and get stronger. It's beautiful, really.
Okay, let's look at a classic example, Grover's algorithm. It's a search algorithm on steroids. Here's how it works. Step 1. You create a superposition of every single possible answer. It's like a flat landscape of probabilities. Step 2. You use a special function called an oracle that knows the answer. It doesn't tell you what it is, but it marks it by flipping its amplitude from positive to negative. Step 3. You use another trick, a diffuser, which basically boosts the amplitude of that one marked item while pushing all the others down. You just repeat that a few times, and pretty soon, the right answer is sticking way up, impossible to miss.
So what's the payoff? It's a massive speedup. For a classical computer searching through a list of, say, 1 million items, it has to check on average half of them. That's 500,000 checks. A quantum computer using Grover's algorithm, it gets a quadratic speedup. It only needs to do about the square root of 1 million checks, which is just 1,000. Think about that. 1,000 checks instead of 500,000. For things like drug discovery, that's absolutely a game changer.
Okay, the theory is mind-blowing.
The algorithms are powerful, but what are we building these things out of? Let's drop all the way to the bottom of the stack and talk about the hardware.
And right now, it is a full-on race. There's no one way to build a quantum computer, and different teams are betting on different horses. The two heavyweights in the ring are superconducting qubits, which you hear about from places like IBM, and trapped ions, which companies like Quantinuum are working on. And as you can see, they each have their own strengths and weaknesses.
Okay, so let's talk superconductors. Their big advantage, speed. They are wicked fast. The operations, or gates, happen in nanoseconds. But there's a catch. They're also really fragile and noisy. They get messed up by the tiniest disturbance from the environment. Plus, the qubits are kind of stuck in place, in a fixed grid, which limits how they can talk to each other.
And then you've got trapped ions. These guys are basically the opposite. They are super high fidelity, meaning they're incredibly precise and don't make many mistakes. And a huge plus, any qubit can talk to any other qubit. It's an all-to-all connection. The downside? They're slow, like thousands of times slower than superconductors. It's a classic tortoise versus the hare situation, and we still don't know who's going to win.
All right, so let's zoom back out. We've got the mind-bending theory, and we've got this early-stage hardware. But let's be real, there's a huge gap between what we can do today and the dream. Let's talk about bridging that reality gap.
Right now, we are smack in the middle of what's called the NIQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale means we have machines with a decent number of qubits, enough to do some cool stuff. But noisy is the key word. These machines are super sensitive, and they make errors, a lot of errors. So they're powerful, but they're far from perfect. And just to give you a sense of scale for that challenge, you know, the big, scary application everyone talks about, breaking encryption. To break something like RSA 2048, which secures a lot of the internet, it's estimated you'd need about 20 million high-quality physical qubits. Today, our most advanced systems have maybe 150. So yeah, we have a ways to go.
And getting there means tackling some monster engineering hurdles. There's decoherence, which is basically the quantum state just evaporating into the environment. There's general noise from all sorts of things messing up the calculations. Then there's the massive challenge of error correction. You need tons of physical qubits just to create one stable, logical qubit. And we haven't even talked about how you efficiently get data into the computer in the first place.
So look, it's easy to get fixated on the big, flashy goals, like breaking encryption. But maybe that's the wrong way to look at it. Maybe the real question isn't when will we have a perfect, fault-tolerant quantum computer, but a different one. What new science, what amazing discoveries can we make with the powerful, imperfect machines that we have right now? That's the adventure we're on today. Thanks for taking this trip down the quantum stack with me.